Um, good morning, guys. Today we'll talk about graphical representations of motion of an object, and we kind of talked about graphs already. You guys know that position time graph, has a slope. So before I even go any further, the two key things that you always want to look for meaning from on a graph are slope and area. Every time you look at a graph, ask yourself, what does the slope of this graph represent? What does the area under this graph represent? So this slope will be change in x over change in t, and for a position time graph, you can see that the slope is velocity. Or if it is a distance time graph, then the slope is speed. The area under this graph, to think of it, if I try to calculate this area, it's a triangle, and this is the base, this is the height. The base is some value, because the area of a triangle is a half times the base, which is some value of time, change in time, times the height, which is some value change in displacement. When you look at displacement times time, or distance times time, that is not any meaningful physical quantity. So we can say that the area of this graph does not mean anything. But for displacement time graph, its slope represents velocity, and its area is not meaningful. Let's look at a velocity time graph. Look at a VT graph, then that's velocity and that's time. The slope of a VT graph will be change in velocity over change in time, and its slope, I hope you can see that slope represents acceleration. The area under this graph, again, if I wanted to find the area of that triangle, area will be a half times base times height. Its base is some time value or delta t, and its height is some velocity value or delta v. So half times the base is time, and the height is velocity. Now, let me not stress about what I'm actually getting, but let me think of the units of what I'm getting. I have velocity multiplied by time. The units of velocity are meters per second, and I'm multiplying that by seconds. So it's as if I'm multiplying meters over seconds times seconds, and I end up getting meters. So the result, whatever result I'll get, its unit will be meters, and I know that result is distance or displacement. So the area under velocity time graph represents displacement. If I wanted to calculate the displacement of an object and I have the graph, all I needed to do would be to calculate the area under that graph. What about an acceleration time graph? Now, since in Epiphysics 1 we're dealing with constant acceleration, all your acceleration time graphs are going to be straight line graphs, representing a positive acceleration or negative acceleration, negative 9.8. So all your acceleration graphs are either going to be straight line graphs like this, or straight line graphs through zero, or they'll just be straight line graphs. You won't have any slope or anything like that. But let's just go with the idea, if we had an acceleration time graph, let's say it was drawn, and we were to have a slope, this would be change in acceleration over change in time. So the slope of that graph, the slope would be change in acceleration over change in time. And I don't know if you can recognize this from this equation. V equals AT. V1 equals V0 plus AT. If V0 is 0, or if I just think of this as the change in V equals AT, then I hope you can see that the quantity change in acceleration divided by change in time I can't find a physical quantity that represents. Let's try to find the unit for area under an acceleration time graph. Area again would be half times the base, which is time, times the height, which is some value of acceleration. If I work out the unit, this is seconds times meters per second squared, which 1 second cancels out with that, and then I end up with meters per second. So I know that the area under an acceleration time graph gives me the velocity of the object. Alright, so that's what we have, the slope of those graphs and the area under the graph. Every time you find a graph, please think about what does the slope represent, what does the area represent. If one of them is meaningless, the other one is going to have some kind of meaning. I know you remember you have drawn all of these different, I think we did them in one of the lessons, the different position time graphs and what they represent. This is very important for you to be able to figure out, because it's going to help us when we start talking about transferring or transitioning graphs. Before we get there, let's first look at what these things mean. I'm going to send you this worksheet so you can fill it out yourselves. So if you have a displacement time graph, the y-intercept of that displacement time graph will be your initial displacement. The y-intercept of the velocity time graph will be the initial velocity, and the y-intercept of the acceleration time graph will be the initial acceleration. The slope of the tangent of a displacement time graph, we talked about this, that's velocity. The slope of a velocity time graph, acceleration. Slope of acceleration time graph, that doesn't mean any physical quantity we know about. If the slope is positive, then that means it is moving in a positive direction. If the slope is positive. If the slope of the velocity time graph is positive, that means it is accelerating. This one is moving in a positive direction, but it is also moving with a positive velocity, because slope means velocity. This one, again, we know for the acceleration time graph, the slope doesn't mean anything meaningful in physics. A negative slope of a displacement time graph, that means that object has negative velocity. This means this one is slowing down, decelerating, speed is decreasing or slowing down. Again, that one is not meaningful. If the slope is 0, that means this object is at rest. If the slope of a velocity time graph is 0, it has constant acceleration. And if the slope of an acceleration time graph is 0, that also means that that value of acceleration is constant. Alright, so if a displacement time graph is a straight line, that means it's moving at a constant velocity. If it is a curved line, there is some kind of acceleration. It's either accelerating or slowing down, but if it is curved, that is acceleration. If the velocity time graph is straight, that means it's moving with constant acceleration. If the velocity time graph is curved, it's non-uniform acceleration. The acceleration is increasing, so it's accelerating acceleration, if that makes sense. We don't cover that in this course, but it will be interesting to look at. If it's an acceleration time graph, there's no meaning. The area under a curve, you guys can fill that out. This word. I can't see that word, so you guys will also figure that out. It is stopped when, you guys will also fill that out, and you have uniform acceleration. So you're just filling out what's happening to the graph. Is the graph curved? Is the graph straight? Is the graph, what's happening? That's what you're filling out. Another important skill is to be able to convert between graphs. So I hope you can see this clearly. I'm going to send you this in your worksheet. This is a displacement time graph of the same object. This is a velocity time graph. This is an acceleration time graph. I couldn't fit all of it in this screen without shrinking it so much. So if I look at this section of this graph, it is moving with a positive velocity. Yes, it is positive because this is a velocity time graph, First of all, since it is above the zero, that means that velocity is positive. However, this velocity is decreasing. Velocity decreasing means the body is slowing down. And if I want to draw the position time graph equivalent of a body that is slowing down from a certain initial velocity, that's going to look something like this. Now, when you're drawing these graphs, sorry, that was too much, something like this. When you're drawing these graphs, you need to be very careful to represent the same distance, because from this position to this position, the distance moved by that object will be the area under this section of the graph. So this part where it is slowing down but having a positive velocity should correspond, the distance value that you write here should correspond, because you're going to do, you guys, the distance value should correspond to the area that you have here. The section from here to here, the object is, the velocity is increasing, yes, sorry, the speed is increasing, but in the negative direction. So it is accelerating, but it is moving in the negative direction. So I'm going to have a curve like that. And again, remember, this area should be equivalent to the distance covered. Fortunately for you, this area is equal to this area right here. So these two parts will just be halves of the same semicircle. Alright, so from here to here, again, this is a constant velocity, so I expect the line on the position time graph to be a straight line, because here it is a flat line on the velocity time graph. This area over the constant velocity should correspond to the distance that is going to move in the negative direction on your position time graph. So I haven't worked it out, and this is too small for me to see, but you will have a straight line with increasing, with displacement that is proportional, or that is exactly equal to the area of this section. Now you have this section, it is accelerating, the acceleration is positive, but the speed is going down. Now calculate this distance. I'm sure this area is the same as this area, is the same as this area. So it's going to be, it's still moving, it's still in the negative direction. So that distance is still going to be covered in the negative direction of the motion. But it will be accelerating. So it is still accelerating, and remember, accelerating means the distance covered increases for each time interval. That distance is increasing in the negative direction. So it's going to be continuing to move negative direction. So I cannot draw, if you have to choose between this curve or this curve, or yeah, because these are the only two that we can choose from, this is the one that represents acceleration in the negative direction. This one means that the distance covered decreases as the time goes on. So it's going to continue to go a little bit like this. Remember, the distance should be equivalent to the time, the area under the graph. From this position to this position, it has zero velocity. Zero velocity means it's at rest. So for the same interval, it's at rest. From here to here, it starts moving, up to here, it starts moving back into the positive x direction. Find that area, make sure it's equal to the same distance that's going to be moved up along this section of the graph right up here. It's going to be moving in the positive direction, accelerating. Constant velocity for a certain amount of seconds. Make sure that area is equivalent to the distance that is going to move this time with a straight line, because constant velocity is a straight line. I don't know where it's going to end, but yeah, that's kind of what it will look like. You guys can be more accurate. Make sure your time intervals are aligned. Mine have not been very aligned. Or have they? Yeah, so like this was supposed to go all the way up to here. And this. Yeah, my intervals are not aligned. You guys work out so that your time intervals are aligned. The acceleration time graph, so look at this. From this position up to this position, what's the value of the acceleration? from this time to this time, it has a negative acceleration. So negative acceleration. From here to here, what's happening is continuing to have the speed is increasing in the negative direction, so still negative acceleration. From here to here, constant velocity, so zero acceleration. From here to here, the speed is increasing in the positive direction, so that is a positive acceleration, so we don't have positive acceleration. From here to here, zero velocity, so zero acceleration. This section up here, it has a positive acceleration again, and then constant velocity, zero acceleration. So I'm going to give you some practice questions and some homework questions so that you can practice how to convert between motion graphs. All right.